Thank you. And thank you for inviting me to be here. I am happy to be here again. So I will start just by giving a motivation on quantitative recurrence and some definitions that you may know just to recall and then describe my model and the results. So starting by the motivation. So the quantitative recurrence, which is a property which have been studied by many authors. So it's defined by estimating the first return time of a dynamical system into a small neighborhood of its starting point. So if we take a point x in the space, we want to look at the orbit of the point by a transformation map T, and the suite of it, the sequence of iterations tx, t2x, t and 1 minus 1 of x is the orbit of x. So we want to see the behavior of this orbit. So if we take a ball of center x radius epsilon, which will be an epsilon neighborhood of x. So by the Poincaré recurrence theorem, we know that there will be a moment n such that the orbit of the system will enter the ball. So that's what we call the first return time. And so we define the first return time of the orbit of x into the ball by the increment n such that Tn of x enters the ball of center x radius epsilon. So the question is to study the asymptotic behavior of tau epsilon as epsilon goes to 0. So we extend the study to include dynamical systems where the time is, in the case of time, continuous time. So that's why we'll talk about flows, especially axiom A flows, and in the case of infinite measure. So that's why we will talk about Z-extension. So start speaking, just telling some definitions for recalling some definitions for axiom A flows. So if we take a C1 flow on a smooth manifold M, which is three-dimensional. So a flow is an application on we have Tx gt of x. So there is some properties that g0 of x equal x, and if we apply gt to a gs, it's gt plus s of x, and this application is a C1 application. So to define an axiom A flows, I need to recall the hyperbolicity. So for a flow, we say that a set lambda in M is a hyperbolic set for the flow if, so of course, the set is GT invariant. And for a point, for any point, for any x in lambda, so there is a splitting of the tangent space in the following sense. We have the tangent space will be decomposed as the sum of a vector space which is generated by the vector field by the flow vector field and a subspace which is where the stable subspace where there is a uniform. So on ES there is a uniform contraction of the differential in the future and an unstable space where we have uniform contraction also, but under the differential also, but in the past. So here there is also uniform contraction. So in the past. Yeah. Dimension 3 for the manifold M. Yes, because after we will have an axiom A flow, which is we will take a disk and it will be the flow will be transversal. It will be codimensional with the disk. So yes. So, so hyperbolicity. So for the hyperbolic set, for example, the Nasab system is an example, but an axiom A flow, it will be a generalization because for the Nasab system, the whole manifold is a hyperbolic set. For the axiom A flow, we need a smaller set, which is called the wandering set. I will define what's the wandering set. So the wandering set, what's a wandering point? So X is a wandering, non-wandering. So X is a non-wandering point. So if, okay, so X is a non-wandering point if you take a neighborhood of the point, so for any t which is positive, so there exists a tx greater or equal to t such that the neighborhood will meet again the initial set. So applied with gtx O is non-empty. So the non-wandering set is the set the number of gt is the set of all non-wandering points. The flow. Okay, so an axiom A flow. So if I take maybe here, okay. If I take a flow on a three-dimensional. Yes, I'm writing it in French. Yes. The three-dimensional on a three-dimensional M is an axiom A flow if the set of its non-wandering points is hyperbolic. And the periodic orbits are dense in its hyperbolic set. I can give an example. An example is if we take a manifold with negative curvature and we take the geodesic flow. So if I consider the geodesic flow on the surface, so it's just an example to give a picture which is immersed in the torus. So the equation is x, y, z such that cosine s so this equation just to give a picture, so it's of negative curvature and I will use this example just to present the results after. So for the axiom A flows, there is the Markov family that yes. Okay. The genus two. Yes. Yes. Okay. So after that, for axiom A flows, there exists always a Markov family. Just also recall the Markov family. And it will be interesting, just you all know what is the Markov family, but it will be interesting to recall it just to see how we will reduce our problem of the return time. So For axiom A flows, there is always a Markov family, which is a finite collection of rectangles. Phi E. So these rectangles are transversal to the flow. So if I take rectangles like this, maybe okay. So the orbit of the system, it means that with this family of finite, which is finite, so the orbit of the system will meet infinitely many times this collection in the past and in the future, so that we can reduce our problem for the flow to the collection, because if we have x here, so we can look at the first return map, to our collection Ex. So if I note x, the union of which is finite, let's say n, so we can look at the first return map, and we also use the first return time. So this will be the first return map to our collection family, and R, which will be the first return time. It's just the first return time here, so T of x, it will be equal to G R of x. Okay, so yes, I must have said that there. So we have the tangent space. There exists a stable manifold and unstable manifold, such that the tangent space, it's the tangent space of the unstable manifold, it's the Ux, and also for the stable. So for the rectangles, yes, there will be stable and unstable leaves, and that's it. Subset of yes, because every rectangle must be in lambda. Okay. So now so with this T and X, I will define the Poincaré section and the Poincaré map. So for an axiom A flow, it will be represented by a special flow over the system xt. So x, it will be the Poincaré section of the flow. And R, we call it the height function or the roof function. So it's defined from x to 0 infinity. It's strictly positive, such that R of x is the minimum time needed to be on our collection. So minimum S, such that GS of x is on X. So T, the Poincare map, which is defined by G of X equal T of X equal G R of X. So I can, for example, put here there will be Poincare section, for example, like this, and several. So this system is isomorphic. So this system X here is isomorphic to a subshift of finite type sigma theta. So we can code the elements on the Poincare section by elements in the subshift of finite type. So in this sense, so if we have X, here's the map T, donc theta, and we'll do like this. So there will be the coding map. Every element is coded by an element in the subshift. So if there is a measure here, if I use the measure, for example, Gibbs measure. So no, not here. Here. So here there will be the measure mu x. I will call it. It will be equal to of mu. Okay. After that, recall also the suspension flow. So we consider the space X R. It will be all the elements X S such that with S so this space is the space where we have all the couples such that this is x0 such that x r of x will be identified by t of x 0 and so on. So so the suspension flow over t with the height function r is the flow psi t which is defined on xr by psi t of s x xs is equal to Tn of x s plus t minus the ergodic sum of r of x. So where n is the whereas n is the unique non-negative integer such that s plus t is uh, between Sn r of x and strictly less than Sn plus 1 r of x. Okay, so these are all the definitions that I recalled. So now I will start by describing the model. So we consider a Riemannian manifold emptied with a sigma finite measure mu tilde such that the flow and P tilde a flow on M tilde which preserves the measure. So if I take the same example there, by taking phi a map from x to z, so the extension T tilde will be defined on x times z, x times z for x t, so T tilde of x t is equal to T x, and phi it will indicate the index which indicate in which cell I am. So if I take the Z extension of the same example that I have, if we have the Poincaré section, so Tx, so T tilde, the extension is defined for an xt in a cell like this. Tx, it's when I am in the next rectangle, and the position it will be controlled by phi. For example, here I will have I will call it because it's an integer, I will call it m. So it will be m plus phi of x. For example, if I see for n t tilde n of xm, it will be tn of x m plus phi of x, phi of t of x, until phi of t n minus 1 of x. So it will be the ergodic sum of phi of x. I have to say something. So M tilde is this will be this we can say this is M tilde, and this Can you copy? It's the manifold M GT mu. Yes, such that this is an axiom A flow. So now we proved a proposition which is the local limit theorem, which we used to prove our results. So I will say it's the local limit theorem. So if we have a two-sided cylinder, I will not like this two-sided cylinder. For all QP that are in Z, so we will see the probability that we are starting from a set A intersection that S and phi equals to 0, and such that we are landing on another set B. So we'll take B, a subset of the positive side of the subshift of finite type, and I will consider the projection of the subshift of finite type into its positive side. So if we take phi minus n, phi k of theta of phi minus 1 of B minus the measure of A. So here there was the measure mu. So here it will be defined the measure plus of B divided by radical n minus k sigma phi. So this will be less than or equal a constant. So there exists a constant C1 positive. So there's a little condition here. This is less than C1, A, the measure of A times the measure of B over n minus 2k. So the condition here is just we have that n minus 2k is greater or equal m0, and the q is so now I will mention the first theorem. Is the almost everywhere convergence theorem. So our aim was to calculate. Yes, theta is the shift map from the subshift of finite type. Yes. 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 In fact, now I will say how we'll prove our results. We will start from a point y in the manifold. Then we will project on the Poincare section. And then we know that x is isomorphic. X theta is isomorphic to sigma theta. So we can work here to deduce produce our results in the manifold. This, yes, this is something that this is a theorem that I proved, and it's local because we are looking at s and phi equal to 0, and we are looking at we are starting from a set and landing on another set. For example, the central limit theorem. We study the case where s and phi is not equal, less than, or equal something. Okay. So yes, just to say the first theorem on the almost sure convergence. So just to recall, we start from a point y in M tilde, and our aim is to study the return time of this point. So we define the return time. So epsilon, it's the infimum t such that g tilde t of y is in the board. Okay, and just state the theorem. Okay, so we have a point y, a neighborhood of the point in the space M tilde. So to study the first return time of this point, we have the first theorem, which is the almost everywhere theorem. Okay, so if we have M tilde, G tilde, mu tilde, which satisfies all the above hypotheses, so we have mu almost everywhere y in M tilde limit as epsilon goes to 0 to log radical tau epsilon over minus log epsilon. It's equal to h 1 over ls plus 1 over lu. And h, it will be the entropy of the measure mu. And ls and lu I can explain. So using the Markov, the rectangles and Markov property. So if we are in the, we can always with the isomorphism of x, t and sigma theta, we can always say that x is coded by an element omega, which is in sigma. No, okay, an omega in sigma. So if we are in the rectangle where we have t and x, if I take the unstable leaf and I return by t minus n to x, so the length between x and the extremity of t minus n of the unstable manifold here. So So this length, we will call it L N U of X. And the same for, we can see the same for Lsn of X. So Lu and Ls are the limits as n goes to infinity to 1 over n ln u, and same for Ls. So now how to prove this theorem? Yes, sorry. Yes, it's log. Thank you. Yes, but it's for the, we can say it's for that map T. Yeah. Thank you. So now, as we said, if we fix epsilon positive, we have S positive, we can see the point Y as GS of X. Okay, that's just which is an empty. So and we also said that the point X, which is in X, can be coded by an element omega in sigma in the subshift. So if we have the Y and its neighborhood, the idea is that we can project on the Poincare section. So the projection of this ball, this is on X, then we can use the coding map to work on the subshift of finite type. So the projection of the ball I call it Px, the projection. So we can see that the projection is contained and is containing a ball of center X or a K so the projection is between two balls, and then we define the first return time on the projection of the ball. So we define the first return time of T tilde to Tx Ts of X epsilon. I call it W epsilon of X, which is the infimum K L is greater or equal to 1, such that TL of X is in the ball and such that Sn, maybe I will say what is Sn, it's the ergodic sum of the Ej of X equals to 0. So I define the return time of the map T tilde to the projection of the ball, and And then we can relate the first return time of y with the return time of t tilde. So there is a lemma. So recalling the two definitions of return time, we have this lemma. So if we take y in M tilde such that y equals gs of x, where s is strictly less than r of x, for almost every y. In fact, the y can be, using the suspension flow, the y is represented by xs, x and xs, and s is less than r of x, just like in this space. So for almost every y, we have tau epsilon is equivalent to the integral of the height function on x d mu of x w epsilon of x. So once we proved this lemma, then it will be the problem will be reduced to study the return time of w epsilon of x. So for this now, I just have 10 minutes. Okay. So now to study the return time w epsilon of x, we can, the idea is to show that this ball is, we will prove two lemmas. The first lemma will prove that for some conditions on the Q and Q prime for a cylinder, we can show that a ball is contained in a cylinder, and also a ball contains a cylinder. We then define the return time on a cylinder and deduce the return time of w epsilon of x. I can state these lemmas. So the first lemma, we prove that if we consider a Q prime cylinder where Q and Q prime are minimal, such that LSQ is less than R. We start from R positive and LQ prime less than R2. Then we can show that the cylinder is contained in the ball. And another lemma, we also take x and x such that x equal chi of omega and sigma. So a second lemma, so for almost every omega in the subshift of finite type, any are positive, so for all m and n that are maximal, such that r is less than the minimum of LU of n, LS of m. So the delta n it's like n minus p positive and an integer. So we prove if we have this condition, we prove that the ball is contained in a cylinder. So the idea after that is there are two lemmas which we define the first written time on a cylinder. Maybe I can take 5 minutes to say this. Here, yes. Thank you. So now the idea we define the first return time to a Q prime cylinder of a starting point omega by tau Q prime omega. It's equal to the infimum n such that theta and of omega is in the cylinder and s and phi of omega equal to 0. So we proved that the two lemmas that limit when n goes to infinity log so we proved that this limit so we proved this limit in condition that we have AB are positive such that 2A plus B is strictly less than 1, strictly greater than 1 over H. H is the entropy of the measure mu, and the sequences Qn and Q prime n are such that Qn is A log n and Q prime n is B log n. We proved a second lemma on the limit. This is the limit n. So there was another lemma on the limit supremum. And from these two lemmas, we concluded with the relations that I gave. So less than or equal 1 over 2a plus b with the same conditions, but with 2a plus b less than 1 over h. So after proving these lemmas, we used the relations, all the relations to conclude the asymptotic behavior of the return time tau epsilon. Okay, so I will not have time to say the everything that I wanted to say, so I will stop here.